Today, we're jumping right into a bit of a medical mystery. It's a story about a super common bacteria, the drugs we use to fight it, and a really interesting puzzle that's hidden in the data. And, this puzzle reveals a much bigger battle that's happening inside our bodies. So let's investigate. So, this is really the fundamental question, isn't it? When you're sick, you trust that the medicine you're given is going to work. But what happens when it doesn't? And I think more importantly, why? Well, that's the mystery we're here to solve today. Okay, so let's meet the subject of our investigation, Haemophilus influenzae. Now, despite its name, it actually doesn't cause the flu, but it can cause some pretty serious respiratory infections. And the problem is, this little bug is evolving. It's developing new defenses against the very drugs that we designed to get rid of it. To really get what's going on, we have to look at the evidence. Researchers at a hospital tested how this bacteria holds up against 4 different, very widely used antibiotics. And the results, well, they were pretty revealing. First up, we've got our champion. One antibiotic was completely effective, a perfect score. Every single bacterial sample was wiped out by it. This is basically our gold standard. Now, for our second drug, there's a big drop. Only 65% of the bacteria were susceptible. So that means for more than a third of cases, this antibiotic is really going to struggle. And here's where it gets really interesting. The third antibiotic, it scored 60%. So very close to the last one, but not exactly the same. Keep that number in mind because it's going to be pretty important later on. And finally, our fourth drug, a really staggering drop to just 30% effectiveness. So in 70% of cases, this antibiotic would probably fail. That is a huge sign of widespread resistance. And here they are, all laid out. You've got the powerhouse ceftazidime at a perfect 100%, all the way down to ampicillin at a pretty dismal 30%. But the real mystery for us today, it lies right here, in the middle, with cefuroxime and amoxicillin-clavulanate. Let's just zero in on these two for a second. 65% versus 60%. I mean, on the surface, it seems like a really small difference. You might even think they're almost interchangeable. But in medicine, those tiny differences can hide some really big stories. So what is going on here? Why isn't cefuroxime just a little bit better across the board? What's the deal with this specific 5% gap? To solve this, we've got to go deeper and look at the bacteria's secret weapons. And this brings us to the really fascinating world of antibiotic resistance mechanisms. These are the clever strategies the bacteria have evolved to fight back against us. You can think of it as their military playbook for survival. In this case, for Haemophilus influenzae, the data shows it's mainly using 2 totally distinct tactics to evade our drugs. So it's not just one uniform army, it's more like 2 different divisions, each with its own specialization. So on one hand, we have the BLPAR tactic. These bacteria produce an enzyme. It's called beta-lactamase, but you could just think of it as a tiny antibiotic shredder that literally destroys the drug. On the other hand is BLNAR, which is a much stealthier approach. This type changes its own structure, altering the very part of its cell wall that the antibiotic needs to grab onto. It's kind of like changing the locks on a door so the key doesn't fit anymore. So how common are these strategies? Well, in this hospital's population of bacteria, 40% use that change in the locks BLNAR strategy. That makes it the most common form of resistance. 30% use the antibiotic shredder BLPR tactic. And the other 30%? They're non-resistant, or what we call susceptible. So here's the crucial point. It's not just about the drug, it's all about the matchup. An antibiotic might be a total champion against one type of defense, but turn out to be completely useless against another one. And here it is. This is our aha moment. This is the key to the entire mystery. The data shows that the BLNPR antibiotic shredder is what primarily stops amoxicillin-clavulanate. Meanwhile, that BLNPR changing the locks mechanism is the main problem for cefuroxime. See, they're vulnerable to different defenses. That 60% versus 65% effectiveness isn't random at all. It directly reflects how common each of these 2 resistance types are in that local bacterial population. So how does this all build into the bigger picture? Why does this tiny microscopic detail matter so much? Well, because a doctor choosing an antibiotic isn't just picking a drug. They're essentially placing a bet. And knowing the local resistance patterns, knowing that, say, 40% of infections in their area might use that changing the lock's defense, it allows them to make a much smarter bet. They can choose the drug with the absolute best chance of success, and that directly improves patient outcomes. So in the end, that tiny 5% difference wasn't just some statistical quirk. Nope, it was a clue. It was a signpost pointing to the really sophisticated and varied ways that bacteria are evolving to survive in this constant arms race. And that leaves us with one final, pretty critical question. We can clearly see the bacteria are constantly changing their tactics. But are we? Understanding these mechanisms is the first step, for sure. But how we use that knowledge to adapt our own strategies, well, that's what's going to determine who wins this battle.